So, in case of DFS, what we know that if this is a corresponding say node is given like that, here from A we are just writing the previous node like that, say BS, say CS, and from this D is a neighbor of A, so that's why we are writing like that. This is EA, say this is FA. So if this is a gold node, this is GD, this is HD. Then what we know that in case of if we consider DFS, then it will first visit this node, then this node, then this one, then this one. It goes like that. If the same case will happen in case of BFS, then the BFS will goes like that. The first this one, then this one, then this one, like that. So BFS is searching level by level, whereas DFS is first goes deeper and then backtrack and then like that. So this is for corresponding BFS traversal. That you know that in case of just a minute. So in case of DFS, what will happen? So we know that in that particular that in DFS, in this algorithm, in this algorithm, we always find that newest node, newest node is first explored. The newest node is first explored. So what does it mean? So this type of approach, this type of approach is known as greedy approach, or you can say this is one type of the greedy algorithm. Why greedy algorithm? Because what do you mean by greedy? Greedy means it will always search for local optimal. It is not search for global optimal. So it may be possible, say if we this is a local optima, there is a global optima. If we only search for we are at that particular positions and we are searching and we find that local optimal, then your algorithm will give that is a solutions. But that may not be optimal because after that there may be some other global optima. But in case of greedy algorithm will always show first the local optima. So in that case, what will happen in case of DFS, it always first explore the newest node. That means it is a one type of greedy algorithm. Also, we find that this algo follows deepest node first. This algorithm, this algo follows. This for DFS. This algorithm follows what I am saying, that deepest node first. Deepest node first. And this is behaving like a stack because newest node means we are just putting the node say S, and then S is popped out, then you are putting B, you are putting C, and you are putting A, then that is the newest node. So you can put in any order. That means it may be possible the A would be putting first, then B, then C would be coming out. So that is the thing, that in case of it is behaving like a stack because the newest node is explored first. So there may be some problem that say we are considering a search space. How search space means if an algorithm is given that from a this is a source node, this is given, and that is a goal node, and your algorithm will coming from source node, it will it will have find the goal node, মানে সোর্স থেকে গোল নোডটা ফাইন্ড করবে। So in case of DFS, if the node is explored like that, if the graph is like that, it will explore this one, and again it will explore this one, again it will explore this one. If the search space is infinite, if the search space is infinite, what will happen? It may be possible that in case of DFS, you never reach to the goal node. Why? Because it goes deeper and deeper, it goes deeper and deeper. It may be if the search space is infinite, then it may be possible that you will never find the goal node. So, the algo goes deeper, the algo goes deeper without notices the goal node, without notices the goal node. So, these are called blind search. That's why this is called blind search. That means not seeing the goal node, I am expanding my algorithm. So that's why if we just place this particular algorithm for searching cases, it may be possible that if the search space is infinite, then DFS will never reach to the goal node. So what I am saying that if the search space, if the search space is infinite, it may be possible that DFS never reaches to the goal node. It may be possible that BFS will never reaches to the goal node. So the thing is that is one of the perspective you can think of that about the BFS and DFS. That means this is one of the perspective that this will not reach to the goal node. So if we take an example that how it will be evaluated, that means if the if we draw the graph, if we draw the graph like that, if the graph is the node is like that, say so now how it searches, first is search this one, then this goes to this, then this goes to this, then this goes like that, then you will find the there is a leaf node, then again 6, it will be searching like that. That means the order I am writing, it will follows that particular order, and the last node is evaluated like that. Now if we consider BFS, the same graph like that, the BFS traversal, so how this is the first node, the BFS will traverse, then this, then this, then this, then this one, this is 7, this is 8. That means it is searching level by level like that. So this is the order if we follow the DFS, and this is the order that we follow for BFS. So if we write the algorithm, if we write the algorithm of DFS, then we know that if we write DFS for some node V, if visited this V is equals to 1, for each vertex W that is adjacent to V, do if this visited W, that means it is not visited yet, then you are calling DFS with that particular node. So if we write the algorithm like that, then we know BFS, we take a vertex, we are explore it completely and throw it away. But in DFS, we take a vertex and start exploring it, and whenever find first unexplored vertex, we again go to exploring that and come back. What I am saying, that what in the previous class we see that in case of BFS, what we take a vertex, explore it completely, because level by level we are explore it completely and throw it away. But in DFS, we take a vertex and start exploring it, and whenever find first unexplored vertex, we again go to explore that and come back. So that is the basic principle. So we can use it for directed graph also. So if the graph is like that, say this is 2, 4, 5, this one is node 6, this is node 7, and say this is a node 8, like that. So we know that visited array, that is initialized to 0, like that. Initially there are 1, 2, 3, 4, 5, 6, 7, 8. So initially these are 0. So first one is visited. So one is visited means this is visited. So in stack, this, if we say this is the content of the stack, so now V is 1, that is a visited, and W is neighbors. Neighbors is 2 and 3. Neighbors is 2 and 3. You just see the algorithm, then you will find initially all visited, which node is visited, that should be make 1, and each vertex W adjacent to V we are putting into stack, and then we have to check that whether this visited thing, that means 2 and 3, are explored or not. If it is not explored, then what do you mean by that? That in the next step you have to visit that, because this one is 0. If visited W is equals to 0, then we call it again. That means we have to make this W equals to 1, and then do the same thing like that. What will happen in the next step? This is the visited array, and we know that 1, 2, 3, 4, 5, 6, 7, 8, that is already been visited. In the next step, that 2 will be popped out from stack, and that is now visited. And what will happen? The stack content is like that. if this is a v equals to 1, this w is equals to 2 comma 3 and 2 is visited, and then what will happen, v is equals to 2 and w is the neighbors of 2, that is 4 and 5. So 1 4 and 5, 1 4 and 5, and in the next step 1 is already been visited, so it will not check, and now we are just visit 4. For node 1, we know visited array node 2 is already been 1, so DFS will not call it, because in that particular visited array, since at location 1 the value is already been 1, that means it has been shown that it has already been visited, so we are not considering 4. Now we are checking 4. In case of 4 it is been 0, so that's why you have to visit this one. So we are exploring like that, then 2 is explored, then 4. That means in that particular state the visited array looks like that. This is 1, this already been 1, 1 2, this is 3, this is 4, this is 5 6, this is 7, this is 8, and the fourth place this is 0, this is all are 0, that will make it 1. And again in stack what will happen, this already v is equals to 1, this w is equals to 2 3, 2 is being visited, now v is equals to 2, w is equals to 1 4 5, 1 and 4 are visited, and since v is equals to 4, that means we have to find the neighbors of 4, that is in that particular case the neighbors of 4 is 2 and 8. So 2 and 8, so we just write that is 2 and 8, and 2 we are checking 2, and from that array 2 is already been 1, so 2 is already been explored, and then we are going to 8, that in place of 8, 8 is 0, so that's why it will visit 8. So if it will visit 8, that means in the next step, that means that 1, this is 2 3 4 5 6 7 8, it's already been visited, that is 0, and this is now, and the stack content is like that, v equals to 1, v equals to 2, v equals to 4, and now this is makes it 1, so v is equals to 8, and w is equals to neighbors of 8. So if we consider the neighbors of 8, neighbors of 8 is 4 5 6 7, neighbors of 8 is 4 5 6 7. So neighbors of 8 is 4 5 6 7. 4 is already been visited, 5 is not visited, so in the next step we visit 5. I am just writing in short. So in the next step, this is 1 2 3 4 5 6 7 8. This is already been 1, this is 0 0 0 1. So in the next step we visit 5, so it makes this 1, and the stack contain v equals to 1, then v equals to 2. I'm not writing all those stuff, we are writing v equals to 8, and now this v is equals to 5. So v is equals to 5, that means you have to, for 5 the neighbors is 2 and 8. So for 5 the neighbors is 2 and 8. So this is w is 2 and 8. You just find that 2 is already been visited, 8 is already been visited, then it backtrack, that means it will show what will be the content left in 8. So we know 4 5 6 7, 4 5 is already been visited, then you have to visit 6, you are backtracking, that means that is already completely done, then you have to backtrack, and backtrack you will find that 4 and 5 is already been visited, but we don't visit 6. So in that particular case you have to visit 6. So now, since this is 1, 2, 3, 4, 5, 6, 7, 8, this is 1, 1, this is 0, 1, this already been 1, this is 0, 0, 1, we are visiting 6, that means we have to make it 1, and so this is v equals to 1, this is v equals to 2, this is v equals to 4, and this is v equals to 5, and now we visit v equals to 6, and the w is from 6. From 6, what we get from 6, there is a 3 and 8, 3 and 8. So from 6, this is 3 and 8. So 3 is not visited, so you have to explore 3. So in the next step, this v is equals to 3 and w is equal to, when you just visit 3, then being the neighbor of 3 is 1, 6 and 7. So we have to write this is 1, 6 and 7. So 1 is already been visited. So what we explore, that 3, so that means this now is 1. So 1 is already been visited. 6, so in place of 6, that is already been visited, but 7 is not visited. So we explore v is equals to 7, and 6 is been explored and 7 is now explored. So now for v equals to 7, we get there is 3 and 8, neighbor are 3 and 8. So this neighbor are 3 and 8. 3 is already visited, 8 is already been visited, so you popped out that. Then we come to the this one, 7 is left, but 7 is already been visited, then we popped out 8. 8 is already been visited, then we popped out. And we see that in case of v5, if we visit v5, then in v5 actually there are 2 and 8 that already been visited, so there is v4. V4 there are 4, 5, 6, 7, all are visited, so it will backtrack and then it becomes none. So what is the order? 1, then 2, then 4, you just see, then you will come to, you are exploring 1, 2, that is 4, then 8. There is another thing which is I just missed, v is equals to 8, then 8, then 5, then 6, then 3, then 7. So this is the order if we traverse with DFS. So if we consider, so this is the algorithm and his explanations. Now we are considering the corresponding space complexity. If we just analyze the place complexity, then so we have an visited array. So we have an visited array. We have an visited array whose size whose size is the same as number of nodes. So in that particular, the page complexity for this array is order of v. So next, memory needed is the size of the stack. Next, we are using stack, so next memory jeta dorkar, that needed is the size of the stack, because we use recursion, and we know that in case of recursions we need size of the stack that depends on maximum distance between two nodes that in the graph. So the size of the stack that depends on maximum distance maximum distance between two nodes in the graph. So all nodes are pushed at least one to the stack. So in the previous example, only node 5 is not present in the stack for some time. It is pushed and popped immediately. But in the worst case, all the nodes of the graph may be present in the stack at the same time. So the page complexity that we need is order of V, because in the worst case we have to consider that. That means what I am saying, that all nodes are pushed at least once to the stack. And in the previous example, what I am observing, that only node 5 is not present because it is immediately pushed and popped out, present in the stack for some time. It is pushed and popped immediately. It is pushed and popped immediately. But in the but in the worst case, all the nodes of the graph may be present. It may be possible all the nodes of the graph may be present in the stack at the same time. All the nodes means V number of nodes. So complexity is order of V. So the page complexity of the algorithm is order of V. So that means that it may be possible that worst case it may be possible all the nodes, if this is a skewed tree like that, this is a skewed tree, then at that time all the nodes of the graph at the stack at the same time. In VFS also, if we consider like that, so it may be possible all the nodes at the queue at the same time, all the nodes at the queue same time. So BFS and DFS, either case, BFS or DFS, the space complexity, the page complexity is order of V. Now if we consider about the time complexity, then if we consider about the time complexity, then what I am saying, that if DFS is in adjacency list, then it is order of V plus E. If we use adjacency matrix, then it is order of V square. That is the, you can say, about the time complexity. You can also analyze the time complexity by using some different factors. It may be possible that you are analyzing the time complexity by using some factor, you can say, about the branching factor. That is the one of the way, by using V, that means number of vertex and number of edges, you can actually analyze the time complexity. But there is also another procedure by which you can say analyze the time complexity. That means for DFS, and if we analyze the complexity with BFS like that. So we know, so we are just considering and taking some assumptions that let branching factor, আশা করি branching factor মানে কি, এরকম যে নোট এর ব্রাঞ্চিং ফ্যাক্টর 3, এটা হচ্ছে ব্রাঞ্চিং ফ্যাক্টর 2, যেটা বাইনারি বলি, এমনি এরকম ব্রাঞ্চিং ফ্যাক্টর হতে পারে. So this is a branching factor. So if we consider that branching factor is constant and let it be B, B is a branching factor, and say depth of the tree, depth is D, we are considering that. So what is the search problem like that, it will be expand like that. it will be expand like that. So if the depth is d and the branching factor is b, then at the last level the number of nodes is b to the power d. If we consider binary tree like that, this is the binary tree. So the thing is that if the last nodes, the question is, I just deviate from that. uh, if the last node contain 4 nodes, leaf node, if the leaf node that contain 4 nodes, then what is the maximum number of nodes? Because we know in case of heap or something else, that is a complete binary tree. So we know this is the leaf node, that we can say 2 to the power n is equals to 4. So n is equals to 2. We can say that. And if, then what we'll find, that if the leaf node contain 4, then the maximum node, that 4, 5, 6, 7. If we say the leaf node contain 8, that means this one, then what will happen? Because this is a complete, we can say about the full binary tree as well as a complete binary tree, then maximum number of nodes if we consider, then we can say this is the leaf node. If this contain 8, then it means the total number of nodes is 15. So from that we can get that if this is a 2 to the power n, that is the maximum possible. So n is 4. So we can say, how can we get that if there is only 4 nodes, that it can be possible that 2 to the power, how much, 4 to the power, we can say the 2 to the power 2 plus 1 minus 1, that is the number of nodes that can be possible. In that case also 2 to the power, so if we say that is 8, 2 to the power 3, that means 2 to the power 3 plus 1 minus 1. So that is 16 minus 1, 15. So that you can use as a formula. Or apart from that, the thing is that what I am saying, that in that particular case, if the depth, this depth, if depth is 2, the number of nodes at that particular level, we know that is a b, this means branching factor, and if this is the depth, then that is 4, that I am saying. So if the branching factor is b and the depth is d, then the number of nodes at the last level, that is b to the power d. So at the last layer there are b to the power d nodes. So and all internal nodes except last layer, all internal nodes except the last layer. So what I am saying, that all internal nodes except last layer, that is b to the power d minus 1, b minus d, if we get approximately, that is b to the power d by b minus 1. So the dth layer contain more nodes compared to all internal nodes in the tree. You can see from that figure that in the last node it will contain 8 nodes in the last level, but all internal nodes there are only 7 nodes. That means the dth layer that contains more nodes compared to all internal nodes, compared to all nodes of the tree. So what will happen? So if we say that a goal node can be anywhere in the last node, so in DFS the goal node can be found only at depth d. It may be possible that we in depth d we can found the goal. This is the best case. It may be possible. That is the worst case, that the goal node or the node you want to find, that will be placed at that particular thing. That means you have to search for all nodes. But it may be possible that we are just going depth wise and the goal node is present here. That means there may be the like that this is a tree or this is a tree, but you are just finding the goal node after traversing depth d. It may be possible that that means we have to consider the average case. So average case is, it may be possible that it is at d plus 1 level, or it may be possible that you are searching last node, you will find that. So average means you have to average this, and approximately that is b to the power d. So the thing is that in case of DFS, the you can say that the complexity is near about b to the power d. In BFS also, in worst case, we suppose that our solution. What do you mean by in BFS? We know we are searching like that. That means level by level. Then you are going to this level. So that means at that level you are just searching one node. In that table, b to the power, that means you are just expanding that. We have to find the solution at depth d. It may be possible that at depth d you are finding the solutions. That means the total number of nodes that you search, that total number of nodes before, because our solution, we are worst case, our solution is at depth d. That means if this is the depth and there are more nodes are there, our solution in the last level. That means we have to search first then b square, then bq, because all level there are, if there are three nodes, then you have to search this three, then and this level, and like that you have to search up to b to the power then, and it is near about order of b to the power d. Actually, if we just do the calculations very precisely, then we can find that bfs by dfs is near about b plus 1 by d. So bfs actually takes a little bit, a little bit large time, large time compare to DFS, but very little bit. So you can say that is the time complexity analysis in different perspective. But actually in our data structure, they will always give you the thing that even considering about the adjacency list and by using adjacency matrix, but that is the one of the procedure that by which you can also calculate the time complexity, where the both case the time complexity is b to the power d, where b is the branching factor and d is the depth of the tree. So in difference perspective,